All right, everyone. I am, of course, Sam Charrington, host of the TWiML AI podcast. And today we're joined by friend of the show, Kamyar Azizzadenesheli, assistant professor at Purdue University for AI Rewind 2021 Deep Reinforcement Learning. Of course, in our AI Rewind series, we talk through the trends and advancements in each of the fields we cover, as well as what's in store for 2022 and beyond. Kamyar last joined us for the Reinforcement Learning Office Hour session we held in conjunction with TWiML Fest in 2020, which was, by the way, a great session. We'll link to that in the show notes. And I'm super excited to have him join us again today. Kamyar, welcome back to the TWiML AI podcast.
Hey, Sam. Thank you. Thank you so much for the introduction. Thanks for having me today.
I'm really looking forward to diving into our chat. You pulled together a lot of great material for us to talk through. The bulk of our time will be spent talking through the 4 key themes that you identified as being important for RL in 2021. But before we do that, I'd love to have you kind of catch us up. The last time we spoke, you had just graduated from Caltech and transitioned over to Purdue. How's that been going?
Well, everything is going well. I was actually visiting researcher at Caltech at the time.
Got it.
It's been an interesting year. So the pandemic part, I would not talk about. It was like a hard part, but excluding the pandemic part, everything was fantastic, and the transition to Purdue was awesome. Building collaborations with many people across the country or across the globe, all of them were like fantastic. Great colleagues here, great friends here, and really enjoyed. And my students are amazing here, so I'm working with them, and we are doing really, really nice stuff these days.
That's great. That's great. Well, to ease us into the topic, maybe you can kind of generally characterize the past year in RL. Was it a big year, slow year, broad brushstrokes? What was your kind of takeaway about the field?
So we had amazing years in 2015, 16, 17, and 18, and in last 2 years we had another like 2 other more amazing years, but it was interesting in the sense that we have made many theoretical development in the last 2 years. From practical standpoint, we have done so many advancements and so many technologies emerged. But if you want me to compare again with stuff happening in NLP, probably we were a little bit less in the media. I would say there were so many great progress in field of RL, but not as much coverage that NLP got in the last 2 years.
And do you think that was just because of the transformative nature of what was happening in NLP, or because the advancements in RL were kind of more academic, less easily applicable?
I think it was mainly so we have made many great advancements in last few years, but these 2 years mostly we've been focusing to harvest them. So there were many well, there have been many technological like advancement. Now we are basically taking them to practice, and there were so many great theoretical advancements, but these days we are actually harvesting them. Basically we are using many of those to make many advancements, and which I don't know, it's like might worth being like flashy and everywhere, but for some reason they did not get to be so flashy. And also in last 2 years, we have been not going to conferences, so we did not
Uh-huh.
get to share with each other what have happened in last 2 years. uh, Unless something is so flashy, they make it to the public easily, but other stuff that we do, they might need it to be kind of communicated among people and get boosted up. But since we're not going around and talking with each other's and meeting and hanging out, and that might also be a reason to for things to a little bit not be that on the media that much.
if you had to pick out, one or two of the kind of most flashy developments in the field, what would those be?
So one of them is this recent adoption of reinforcement learning methods in robotics. In robotics, in the last 2 years, I've been observing. Okay, despite the fact that many researchers were not able to go to their labs to run experiments for robotics, uh, there have been great progress in the field of robotics, mainly due to the deployment of RL methods, or I would not say deployment. The people in the field of robotics are so great in knowing topics in RL that they develop RL algorithms for their problems, and these the developments actually made it possible to make many fundamental advancement in robotics. For example, now you can have drones flying weirdly with all everything guaranteed, and like not just plug and play, everything is guaranteed. You can have many robots actually walking in different trains, and mainly all of these things are been made possible using learning methods. So this is one flashy thing happened last year.
And actually, let me pause you because that's getting into one of the areas that you identified as a theme. So let's just stick with that for a second and dig a little bit deeper. We'll include in the show notes links to a bunch of the papers that we'll be talking about, or as close to all of the papers that we're talking about and demos as we can. So be sure to check out the show notes. But you mentioned with regard to the drones that well, there's one paper and video that we'll share that's kind of high speed RL controlled flight through like a dense forest that was really interesting. And you just mentioned guarantees. Talk a little bit about the guarantees aspect of that. What is that offering?
So that's a very good question. It has two folds to it. Many people in robotics, when they want to deploy an algorithm, they want to make sure that algorithm works guaranteed, not just by chance. They want the algorithm to be there and work for sure. Okay, so this is one of the things that they actually need for many applications. You might call it cultural thing. It has been there for like many decades, and if you want to propose an robotics algorithm that is acceptable to roboticists, basically they most of them they require you to provide a guaranteed algorithm, or basically guarantee that your algorithm works. And so the good thing is, one of the things that prevented roboticists to adopt methods we develop in machine learning was the fact that they were not seeing a way to get guaranteed algorithms out of them. Okay, but in the last few years, there have been many amazing researchers in robotics with robotics and control background who are now, I would say, expert in machine learning. They can develop algorithms in some topics way better than I would do, and they are actually behind all this improvement and advancements, and they are able to deploy and develop reinforcement learning or general machine learning algorithms that can be used in robotic control that is actually guaranteed to work. And what happens when things are guaranteed to work is, for example, you can if you have an algorithm which is guaranteed to work, you can deploy it in a very extreme scenario. For example, extreme unknown wind. You're having a drone which is supposed to fly in a weird situation, and if you have an algorithm which is guaranteed, I'm not just saying like some guaranteed, they are actually guaranteed to work right away. You just plug and play. You just deploy the algorithm in the wild, it works. Okay. And you don't need to crash your drone, and it might cost you millions of, not millions of, like thousands of dollars. And you don't need to spend so much time tuning. Everything will work right away. So this is one thing that roboticists they would like to have as for their algorithms.
What's the next level of detail or kind of technical detail around a guarantee? Like it strikes me that that's fairly ambiguous. It could be, are we talking about guaranteed convergence, guaranteed predictions around control within a certain range, or something else.
Okay. So the guarantees are mainly about the stability and the
Okay.
performance. Okay. So when you come up with a policy to control a drone, one thing you really one thing that practitioners would ask you immediately is, would you guarantee that this controller is stable? Means like it's not gonna, or you have a walking robot. Can you guarantee that this controller would not crash the robot, would not fall, would not hit, or the action that, okay, in the control system the actions can go to infinity mathematically. So do you have a guarantee that your machine is not going to overshoot to some unknown region? Okay, for example, if you have a drone, you're not going to have like a power of 10,000 times what is allowed, and to the drone, and drone might crash. Okay, or the engine might just burn down. So these are the types of guarantees for the stability. And the performance guarantee is like how far you're from the what you actually your desire to be. Okay, so this is, for example, if I have a drone is going to fly, like to do weird maneuver in extreme wind and follow a specific like pathway, can I guarantee that this drone would do that if I use a machine learning model inside the closed loop control? Okay, so these are like type of guarantees that we are talking about.
And what are the techniques that have been developed that allow us to now provide these kinds of guarantees?
One of the coolest one I'm aware of is the notion of Lipschitzness. So if you have let's say deep neural network to model, um, so let's put it this way. I mean, I can talk about one of the works that I'm fully aware of. So let's say you have a drone. This drone is trying to land, okay? And when this drone gets close to land or it gets close to ceiling, this air circulation, the circulation of air through the wings of the drone, imposes many weird fluid dynamics based pattern that's Newton's law would not easily give you. Okay, Newton's law that you have actually put in the motion equation for the drone. So those are not there. Okay, so can you use machine learning models to learn this residual pattern or whatever is this thing, this circulation of air results in the drone maneuver, and can you learn those things using deep neural networks? That's we know we can learn. But the thing is, can you make sure that these neural networks that you're using is Lipschitz? If this neural network is Lipschitz, which you can use some techniques like self-normalization and or other techniques that make sure that the neural network is Lipschitz, given this, you can actually prove that whatever controller you get is going to be robust. Okay, this is one of the things you would get as a guarantee.
Your ability to guarantee that the neural network is Lipschitz is around the way you formulate the your cost functions and things like that.
You formulate the cost function and the architecture.
Mm.
Okay, so both of them together. I don't want to have soft guarantee. I want to neural network. If I put it in the cost function, it becomes a soft guarantee.
Okay.
I want to put it built in the architecture that is going to be for sure a Lipschitz function. Okay, and I want to know what is that Lipschitz constant. If I know all of these things, I can go and design a controller. Okay, but the result of it is going to be, after doing all this training, the first time you deploy the machine in the wild, means that the first time you deploy the drone or a robot in the wild, it's
Mm-hmm.
going to work right away. Like, you don't
Yeah.
need to spend like 2 months or 5 months or 2 years of fine tuning.
Now, historically, one of the things that has prevented us from, taking things out of training and putting them into production and having them work right away is the whole idea of, call it what you will, generalization, domain adaptation. Like the real world is different from the environments that we train on. Does do the? It sounds like the guarantees are strong enough that they overcome that issue. Is that the case?
It is the case, and also the expertise in roboticist, like machine learning expertise in roboticist researcher is a second thing. For example, this problem that you brought up, that when you train things in the lab, and when you change the situation, things break down. The recent advancement that people in robotics made is like this new era of doing some sort of online meta learning on the fly. So there are many algorithms they proposed recently that you actually can learn a setting that can adapt extremely fast to a new scenario. For example, that wind condition problem I was talking about, you are flying a drone in extreme wind scenario and the wind keeps changing. Okay, well, I mean, in your training you probably had like 5 or 10 wind condition, but in the wild it's keep changing. It's going to create this turbulent flow. It's going to be extremely hard, and they're unknown as well. They can be adversarially chosen too. Okay, can you come up with an algorithm which can adapt to any wind condition on the fly? Okay, so these, for example, one of these cool algorithms with, again, learning theoretic guarantees have been developed by roboticists and control theorists who are extremely well and expert in machine learning. So basically, this okay, there is a general theme and trend in reinforcement learning these days that people use the basic topics and core topics in reinforcement learning and take them all and develop problem specific algorithms. Okay, this is one of the general theme these days in reinforcement learning. 8 years ago, when I was doing reinforcement, I started doing reinforcement learning, we were like, okay, find the hardest problem ever could exist and try to have an algorithm which solves that. Okay, this was a theme when I started working in reinforcement learning, and was a main theme for many, many years, to come up with principled algorithms which actually works for a worst case event, like not even Earth or universe, like whatever can mathematically be hard is going to work for that. But these days people are like, hey, let's use all those principles that we have developed in the last, I don't know, 30 years or 40 years, and take them to design and develop problem specific algorithms. So this is one of them. Like you want to fly drone, and you want to be fast and adaptive, you want to be robust, go and design your R algorithm. Given those principles, design your R algorithm to do such. So this is a interesting that I really like.
And I'll encourage folks once again to check out the Learning High Speed Flight in the Wild video. It is super impressive. That drone is going fast, and the trajectory is a lot smoother than, if you saw a drone, ML controlled drone video a couple of years ago. It was like a lot of stops and starts and things like that. This is pretty smooth. The robotics topic that we were just talking about is related to another area that you identified as a key theme in RL over the past couple of years, and that's advances in control. Can you talk a little bit about what you see happening in control?
Yeah, definitely. Well, control theory arguably is one of those oldest settings or problem study that I firstly asked about how we can come up with a policy that can do something. Okay, so the field of cybernetic, it used to be called, was around this idea that how we can actually come up with a way to control a system. And this problem has been there for almost ever, and you can find books that are like haven't been open for like last 60 years. This is how old is this topic. And so but the thing is, this topic, this problem of control theory has been there for a long time, and there have been so many improvement and amazing developments in that field. But recently, specific in the last 2-3 years, uh, many reinforcement learning folks, they were, and basically learning theory folks, they were asking, hey, most of the almost all of the control theory is about the setting that you're not going to learn anything. Everything is given in advance, and there's no learnings involved. So I give you a model or the environment, the parameters, everything, and I ask you to come up with the optimal controller. Of course, there are settings like adaptive control that you would learn, but those settings were not that established yet. Okay. In last few years, many of us started to learn many things in control theory, and try to see whether we can frame them as reinforcement learning problems. Okay, so now in this problem that's like 3 years ago, we were like, we don't know how to solve control problems when we don't know and we don't know the environment. Now we actually know a lot. Today we know a lot about how to control um, a control system uh, without knowing the parameters of or how the environment works in advance. Basically, we literally turn the problem to a reinforcement learning problem that things are unknown in advance, and you're going to uh, interact with the system, learn how the system works, and given that, uh, come up with a good controller which actually can stabilize the system. Stabilize the system means the system does not blow up, and maintain some guarantees that you want. Okay, so this was one of the things that happened in the last few years, and it's a theme because it's one of those areas that machine learning got involved, and control theorists, they were kind of extremely welcoming, and they are now there are many works in this area of learning and control that actually derived by control theorists that I'm extremely excited. And we actually have a new conference called L4DC. So this is a new theme of research that basically goes back, and okay, there are many problems in the world. There are control theory problems. The nuclear power plant, you want to control it, you need to have a control theory problem solution. You want to send human to Mars, to moon, you have a control problem there. If you want to like I don't know, anything, or you want to control
Any of the robots we were just talking about.
robots, or this big things that like data centers, the cooling of data centers,
Mhm.
you want to control those. Basically all of these things are control problems. But what the new theme is like, hey, great. Back in the time, people were going and analyzing the model and come up with the model themselves, and then design the controller. Now what we
Yeah.
are saying is like, hey, you don't need to spend 5 years doing that, you or doing like designing or understanding the model. Just give it to the RL algorithm, it would do it. And the question is how the RL algorithm would do it. These are like these are the things that researchers these days are working on, and they have developed many algorithms for, and some of them are really surprising, and some of them are changing the topics. Basically, for example, there is a topic in control theory called robust control, which is it's been main thing for control theory for almost ever. And recently, in like last 2 years, we actually altered the definition of it. We were like, okay, robust control, fine, but we don't want it.
Well, what was it? What did it mean before, and what does it mean now?
So the thing it was saying before was, okay, you have a, I give you a system to control. Okay, I give you let's put it in the RL context. I give you an RL environment to sorry. I give you an environment that you don't know exactly how the environment works, but I give you an estimate of the environment. Okay, but the true environment is going to be slightly away from this environment. Okay, so now the one question you can answer is like, can you come up with a policy or controller which is going to, when I apply that controller, is going to work for even the worst choice of these environments. Okay, so I have like, I give you an estimate of the environment, but the true, I also tell you the true environment is like somewhere close to this true to this estimated environment.
And when you say an estimate of the environment, is it the state of the environment that is unknown, or is it the, whatever you're trying to optimize, the score or the performance or
Let's say the dynamics of the environment is not clear to you. Okay, so if I have a cup of water in my hand, if I want to lift it, I would expect the glass go like 2 centimeter up, but it might go 1 centimeter and a half. Okay, so this is the uncertainty I have about the environment itself, or uncertainty I have about the environment noise. There's a noise in the environment. I have uncertainty about that. Okay, so these are the things that are not modeled. Okay, but basically these are unknown to me, so I don't know how exactly the environment works. in my mind, if I lift this cup of water, it should go 2 centimeter up. But when I apply my action on this environment, the cup of water goes up 1 centimeter and a half. Okay, so this is basically, there's a discrepancy between what happens in the world and what you have in mind. Okay, so the robust control says you have an estimate of the model in your mind. The true environment is not the exact estimate you have. The true environment is somewhat close to it, but you don't know which, how, like, what is it. But what you do, you make it a min max problem. You try to find a controller which works for the worst possible that can happen to you. Okay, so when you come up with a controller, when you apply that controller, the environment might be a good environment or might be a worse environment around the estimate you have in your mind. Okay, so you were trying to come up with a robust way of doing it. You were saying, okay, I don't know what is the true environment, but I know it's close to the estimate I have, so I try to find the worst environment possible close to my estimate, and I try to be best for that. Okay. Okay, so it's in somehow what it means is like, whatever controller you're going to use is going to do somewhat good for any environment in this set of environments that are possible. Okay, so this was a robust control that has been like there since like 60s. Okay, so basically solving min max problem. I don't know how the environment works, but I hypothesize is going to be the worst possible that can happen to me, and I want to find a controller which actually solve all the environments there. Okay, and this one is going to be bad in the sense that if you want to robustify yourself against the worst thing that can happen, the control you are going to get is going to be really, really, really conservative. Okay, but this was a practice for like 60 years. Yeah. Okay, but in last 2 years we were saying like, hey, good, fine, you can design a controller at the beginning which is going to be robust to whatever is going to happen in the future. But if you run your controller for 10 time steps and you realize that the environment is not that bad, update it. You don't need to keep running that very, very, very conservative controller for next 55 billion years. After like few time steps, if you realize that the environment is not that bad, you don't need to robustify yourself against something that is worse. You can just robustify yourself against the worst is going to happen, not the worst that would have happened. Okay, in robust control, we are saying that I want to be robust against the worst that could have happened to me. But what we have been saying recently is like, hey, you don't need to be that conservative. You just make yourself robust against what the worst is going to happen to you.
So it's kind of like you, based on the observed data, you try to identify a distribution and be robust for that as opposed to the
Yes.
worst possible.
Yeah. Yeah. If worst possible is there, but if I interact with the environment, then the uncertainty is not that bad. My estimate is not that bad. Just update myself, be more relaxed, and this is going to work in practice very well. So this was one of the themes that I really liked happened last two
Nice.
years.
Is there a name for this? It sounds like it should be called meta robust learning or something
Yeah,
like that, or
it's
meta
called.
robust control.
I think it's called improper learning and control.
Is that the improper learning for non-stochastic
Yes, yes,
control?
by Elad Hazans and his group and others. Yeah.
One of the things that I saw in taking a look at that paper was they talked a little bit about this kind of arc in control from classical control, which you described earlier, like all the parameters of the thing that you're trying to control, to stochastic control, which there's now some noise in the system, but it's kind of random noise. And this paper was really geared around non-stochastic control, which, as opposed to assuming just kind of noise injected, it assumes like adversarial perturbances. Um, is that non-stochastic control formulation, is that newer? And can you talk a little bit about this, like assumption of adversarial perturbance versus noise?
Yeah, sure, definitely. So this you in that paper you make this assumption that things are adversarial because you want to be robust against the worst that can happen to you. So assuming things are adversarial has been there in control forever. Okay, but they were saying you don't need to robustify yourself against the adversarial noises or adversarial changes or perturbation in the model without looking what happens to you. They were saying that, hey, look what happens to you, and you can adapt to the to the adversarial noise as well. So this was the one of the things. But when you make things noisy, basically you make this thing to be a stochastic noise, you can do many things. And making things a stochastic noise has been there forever. Like when we sent human to moon, we used a model called LQG, linear quadratic Gaussian. Yeah. So this model basically solved by Kalman and others back in age of dinosaurs many years ago. And So this model, this solution, sorry, this setting is noise is a stochastic, and you're trying to come up with a controller for the setting that the noise is a stochastic. Okay, so the noise in the system is a stochastic, it's not adversarial. Okay, so, and Kalman was able to give a solution to this problem. So you know the environment, yeah. So you know the environment, you know the noise is Gaussian, and for that you can come up with the optimal control design. Okay, and people did it. People sent human to moon with this exact solution. But the interesting thing is, now assume that for the same model, I don't tell you what is the what are the parameters of the model. I don't tell you what is the dynamics. Can you use data to learn the dynamics? It's a basic machine learning question. I dug down so many books from many years ago. I talked to many colleagues in control theory. There was no solution for it. If I give you the few samples and I ask you, hey, can you estimate the model parameters of that thing we used to send human to moon? I couldn't find anything. Yeah, okay. And this was another big innovation in machine learning and, well, intersection of reinforcement learning and control that happened like 2 years ago, and also keep happening and last year and also these days, that people are now actually proposing interesting and weird and cool algorithms to be able to learn the parameters of the dynamical systems that are heavily used in practice. Okay, so these are new things. Like now we know how to learn the model of that system that we used to send human to moon. Okay, what does it mean? It means that now if you want to deal with a new system, so for that system we had like many years of experience, many like hundreds of engineers. They were like tweaking things to come up with the parameters. Now with this new machineries that we have, you don't need 5 years of engineering and hundreds of engineers to go and tweak things to see what are the parameters of the model. You can directly deploy these algorithms to actually directly learn the parameters of the model. So the machine itself learns everything, which is like very exciting.
And is the paper that is uh, that best exemplifies that, is that logarithmic regret bound and partially observable linear dynamical systems?
That's a paper that first proposes how to learn the dynamics of this partially observable control systems. That you were saying there's a noise in the system, you don't observe everything, the state is noisy and you don't observe everything, which is the same model people use in sending human to moon. And for that setting, this paper actually shows how to learn the parameters of the model. And the interesting thing is, like, after being able to learn the parameters of the model with the algorithms proposed in that paper, you can actually get a controller which controls the system without knowing the system in advance, such that the performance is almost identical to the performance of the optimal policy. So this algorithm learns so fast, basically exponentially fast. It learns everything, the optimal controller, exponentially fast, which is kind of weird. And it's able to do that, which is like, I like it a lot.
And is the learning the environment and learning the controller, is that happening in parallel? or is that or like in the same loop, or are they serialized steps?
In the same loop. They happen in the same loop. And interesting observation there is, in order to come with a good controller, you don't need to learn the model very well. If you have some idea about the model, you can come with a really good controller. That was another observation in that paper. That Yeah, you learn the model with a rate of 1 over number of square root of number of samples, but your controller would converge to the good controller exponentially fast, which was another cool thing.
That strikes me as counterintuitive in the sense of learning a controller has been hard for a long time, even when we were given the model. And so, how is it that not knowing the model and kind of learning it, but not very well, gives us good performance and allows us to learn a good performing controller?
That's a very, very good question. So it's like you don't know exactly what is a model, but the cost function here is something convex. Okay, so we're talking about linear quadratic Gaussian. So the cost function is quadratic. It's called regulatory cost, in the sense that it's quadratic in the sense that if you're away from it, you get penalized the distance squared. Okay, so if you're too far, you're gonna get penalized even higher. So now you have a model, some estimate of the model, you deploy your policy, your controller in the real world, and the deviation is large. Okay, your model is not accurate, but when you deploy a controller on the environment, the deviation you get is large. So you are not going to use the optimal policy of the model you're using. You're using a policy which gains some information about the model you learn, such that when you apply it on the real world, is not going to deviate too much. Okay, so it's like kind of different from the paradigm we have been using in classical reinforcement learning algorithm, that you come up with the estimate of the model and then build a confidence interval and find a model in that confidence interval, and then find a policy for that model. This was a paradigm we have been using, but in this paper we were saying that no, you estimate the model, good, use this controller that is going to do well on this environment on the real world, and if it's not performing well, make it better, despite the fact you don't know the real world.
Almost like the initial estimate of the model is like an initialization as opposed to something that you're fixed on.
Yes, yes. So you have a initialization of the model, and you have basic estimate. You come with the controller. You apply that controller on the world. Take 5 samples. You see the deviation is really large. What you do not just keep looking at it. You update it. You update it. How you update it? Gradient descent. You literally do gradient descent to update it. And the controller here you come up with is actually gradient descent based controller. You don't do anything fancy. You just do SGD. Everything works. Yeah, this was another cool thing happened, and these works actually opened so many new doors for many people in control theory and reinforcement learning and in general machine learning, that now they can, given these tools, you can go and develop many things. For example, knowing how to learn these partially observable linear dynamical systems. So these settings are partially observable linear dynamical system. They're linear because dynamics is linear. They're partially observable because of the example you gave. Then the state is noisy. You don't exactly observe the state. Now people are developing all sorts of algorithms for these settings, because now we know how to design a controller, and we also know how to learn the dynamics. People took this stuff to nonlinear control as well. So now we also know how to control nonlinear control problems. If this interview was in 2 months, I could share many weirdly cool news with you, but maybe next time.
Awesome. Awesome. One of the other areas that you identified is risk sensitive RL. Talk a little bit about the shifts that you've been seeing in the way we're optimizing these RL problems.
Yeah. So this is very good, and I hope that the audience would also see it. I kind of, sometimes my friends, they told me that I'm good at finding these seeds happening in machine learning field that start growing and blooming, and I hope that my prediction is correct for this one as well.
This is one of them.
I think this is, I'm going to make a prediction, but I made so many predictions before they worked. I hope this one works as well. Uh, if it doesn't, I apologize for those folks that were looking for something which is going to be big, but turned out not to be big. But okay, let me convince you.
It
And
sounds like an important area.
it is, it is,
So I'll let you go ahead and describe it.
it is insanely important. All the machine learning we have, not all of, almost all the machine learning stuff we have been doing in the last, I don't know, 80 years, they were around this idea that, hey, I have a loss function, I want to maximize it or I want to minimize it. How I'm going to evaluate it? Look at the accuracy. This is what we have been doing in supervised learning. In reinforcement learning, give me an algorithm which maximizes the expected return. What I care is expected return. Now you come to my office. Let's assume that I'm a healthcare practitioner. You tell me you have a prescription drug machine which is going to have 90% accuracy. Okay. I would ask you, hey, what happens with that 1%? Are you going to make a small mistake or you're going to kill the person? Okay. So it's like the expected value of your return is not the thing I would care in practice. I would care how you would do in different parts of the tail. Okay, so if you're doing your you're doing 90%, your expected return is like really high. Good. What is your variance? Is variance? Let's assume I'm a hedge fund holder or whatever it's called, hedge fund manager, and you give me a policy and you tell me, hey, if I use this policy in expectation, I'm going to make $5 billion a year. Good. And I ask, where's the variance? The variance is like, or the standard deviation. If the standard deviation is like 10 billion, then I'm not going to use it. Okay.
Right.
Or if like if you tell me this is the variance, let's assume the variance is also low. But if I look at the if I apply your policy in the real world, I'm going to make money every day, right? Some different money, or I can lose money every day. But if I look at 10% lower quantile, if it is going to be that 10% lower quantile is going to be like humongously low, or these are like examples. Or if you are deploying a policy in a societal setting, or judiciary system, and you say, in this city I use this policy to do to help judges, and then you say, okay, the crime or the wealth of the people in the city increased by 10%. Okay, great. But now I go and see like 5 people in the city became billionaire. Okay, so the expected value is not that important. Variance also might not be that important. 10% or 5% or even 1% upper quantile of my distribution was important. Okay, so these are the things. Like now, you give me a classification algorithm. I apply it on my problem. Great, but I want to know what is the top 2%. When I show an image of a dog to you, you tell me like you misclassify it, how bad you misclassify it. Okay, so these kind of things that actually we care about the distribution of our performance, not just the performance itself. Okay, so now what I think is, now also I've been working on it in this area, is like, and also there's so many works just happened last 2 years. Weirdly, just last 2 years there have been like bombarded of papers in this area, that people are asking, hey, can I have a machine learning algorithm that is able to actually maximize different risk functionals instead of just expected value? Okay, this is one thing. Another thing is, given my machine, can I evaluate the performance of my machine with respect to all sorts of risk functionals? Okay, before you were going, you, as if I'm a healthcare practitioner, you give me your policy, and I was going to look at the past data and see what is this expected performance. Now the question is, can I look at the top 10% quantile? Can I look at this variance? Can I look at top 50 quantile? Can I look at different weird things about it and decide whether your machine is good or not? So these are things that I think people in practice need. This is aligned with that idea I was, or theme I was saying, that we are these days we are trying to develop a specialized machine learning methods. So for here, we're trying to come up with the specialized methods that practitioners, let's say in healthcare or in the stock market, would be able to use. Let me give you this example. There are I asked 20 companies to give me their drug prescription policies, and I'm CDC. I'm going to adopt it. This is a hypothetical example. And now what I would do, I look at these 20 machines. I look at their expected value. I look at their variance. I look at many different risk quantities, and based on all of them, I'm going to decide which one is better. So first question comes up is whether the thing I'm doing is the statistically valid or not. If I look at 10 billion different tests and run the 10 billion tests on these 20 machines, the result I'm going to get are going to be valid or not. These are like questions that people have been trying to answer these days, and they have been trying to ask. Similar with reinforcement learning algorithms.
It sounds like this is a broad movement or trend that you're seeing in machine learning. In the RL setting, how is it accommodated? What are some of the things people are doing?
Oh, okay. Actually, the interesting thing is most of the fundamental development happen actually from RL, which
Having
are,
an RL first?
yes. So, for example, this idea of like, so for this idea of this healthcare setting,
Mm-hmm.
you give me your policy. I want to evaluate the performance of your policy with respect to all the risk functionals.
Okay.
Okay. So this is a contextual bandit problem. That
Mm-hmm.
the topics I'm talking about, there are mainly, or so many other risk functionals. People have studied these things in the context of RL. People have
Okay.
studied in MDP and contextual bandit. These are what I am aware of, and there are so many impossibility results. There are so many positive results when you're using different risk functionals. That there are many things out there coming from reinforcement learning, and now people are getting ideas and generalizing to general machine learning settings.
Okay. Oh, interesting. Interesting. Uh, can you give us an overview of some of the specific papers and the specific things that they're trying to accomplish?
Yeah, just one another point. The reason it actually emerged from reinforcement learning is most of these things arise when we are talking about decision making. If I'm going to come up with a policy for society, or if I'm going to come up with a policy to be used in healthcare, I'm solving a reinforcement learning problem. So these type of questions basically came from reinforcement learning settings. Another example I give you, in supervised learning, we don't talk about safety much. Okay, safety is another constraint where we need to have. This safety mainly is talked about and developed in the field of reinforcement learning. I'm pretty sure people are taking these things to supervised learning as well, because in supervised learning, safety is important, but these are more important issues in reinforcement learning. Yeah. So these are basically some of the reasons why these things emerged from reinforcement learning. Some of the papers. So there are some papers that actually talk about this risk functional that Daniel Kahneman and his colleague, they came up with this prospect theory that you would prefer to lose less than gain more. Basically, this whole idea of prospect theory is like, if I give you $10 more, you're gonna be less happy than if I get $10 from you. So this idea says, hey, you don't care about expected value. If you earn more, you're gonna be less happy than you are going to lose the same amount. Okay, so therefore the expected values, they don't sum up. If you lose more, you're gonna be really angry. If you gain same amount, it's not gonna compensate.
Right. So loss aversion should have a higher impact than the possibility of gain.
Yeah, so yeah, exactly. So these are the things that, now if that's the case, if I want to come up with an RL algorithm for MDP, for contextual bandit, if I consider these things, what can I say? Can I find, is it possible to learn a policy which maximizes the prospect theory objective function? Can I find, or there are impossibility results? There are some other things which come from KL divergence stuff, which says if you make more, you're gonna be basically the same thing. If you make more, you're gonna be less happy than if so. If you have some certain amount of money, if you make a little bit more, you're gonna be more happy than making so much more. Okay,
So
so it's
kind
not
of
linear.
marginal
Saturating.
utility
Yes, exactly.
or that kind of idea. Yeah.
Exactly. So if you're gonna use some ideas like that, can we get algorithms
Mm.
working?
Hmm.
So these are like risk specific settings. There are some other people working on the area that say, hey, you're interested in prospect theory, good for you. You're with this interested in this exponential stuff or this marginalized benefit stuff, good for you. Can we have a theory which actually answers question with respect to all possible risk functionals ever developed? Okay, so in insurance premium design, there are people, they talk about some risk functional called distorted risk functional. What is this? It just takes different part of the quantile and distort it and come up with the and then do the expectation of that distorted reward basically. Okay, in risk management, they look at things called CVAR. So what is CVAR? It looks at, let's say, expected value of your return of the 10% upper quantile. So I don't care what is your expected value you're going to make. If you are going to lose, means the 10% lower quantile, what is the expected value there? So
Hmm.
this is another thing that people use. It's called uh, worst.
Conditional value at risk, the CVAR.
Yes, yes, condition value at risk. So condition on that you are in lower 10% of the quantile.
Hmm.
What is the conditional value of your money at risk? Okay, so these are
Mm-hmm.
the things. My company cares about quantile of 10%. Your company cares about 15%. My company might care about 15%, 12%, 13%, 14%, all of them. Okay, my company might also care about the distorted risk functionals. My company might care about prospect theory risk functional.
And is the idea to be able to decouple any particular problem from the specific loss function or optimization function so that you can kind of get results for multiple ones at the same time? Like, how exactly we're formulating the problem here?
That's a very good question. Now, let's say I give you the past data set. My company has been working in healthcare for last 10 years. I look, or last 5 months, and if I'm lucky, last 10 years. So I have 5 years of data, and now you give me many RL developed policies, and I need to look at the performance of these policies with respect to all these risk functionals. And then I want to, so you give me 20 policies. I use this data set to evaluate the risk performance of all these 20 policies with respect to infinitely many risk functionals. Who designs those risk functionals? My experts in my company. They come up with all these risk functionals that, or tests basically, and or one of my expert says, let's look at the CVAR of 10%. Another one says, let's look at CVAR of 15%. I take these 20 policies and apply it under my data and estimate all these quantities. Okay, and after these guys seeing all these numbers, they might come up with new tests, and they might also, after seeing those the result of those tests, they might come up with many new tests, and then in the end they might choose one of these policies. Okay, so this is the setting. I have this past data from like last 5 months. You or some other companies, they give me 20 RL policies, and they tell me these are good. I'm going to go and talk with my expert to see whether they are good or not. So I'm going to use these policies and apply it on my past data and see how they perform with respect to all these risk functionals.
I'm still not. I'm not very clear on what makes this interesting from an RL perspective. Like the first thing we talked about was, it's clear why that'd be interesting and important. You want to develop a policy using RL. You used to do it based on maximizing expected reward, but there are all these other things that you care about. How do you do those with RL? This second problem sounds like you have a policy. It could be RL policy, it could be any policy, and you're just kind of chugging your past data through the policy and evaluating the results. What am I missing there?
The first setting is called online setting, that you're actually using your RL algorithm to design and come up with some policy. So these are those papers I talked about, that they look at the different risk functionals. The second setting I'm talking about, that you have 20 policies. They can be expert design policies, they can be RL policies, whatever policies. This is called offline setting, or off policy setting. So I have the data, you give me policies, I want to evaluate them first before using them in practice. Okay, so I want to assess their performance before using them in practice. So this is, we call it off policy risk assessment problem. So, or in short, OPRA. Is like you have off policy data from the past, or log data, and you use that data set to actually assess the performance of your policy. Okay, so this is a whole topic of off policy setting. We have off policy evaluation, we have off policy improvement. Means that I give you past data, I hire a new person, I show that person my last 10 years of data, that person is supposed to give me a good policy. Okay, I'm not going to allow that person to deal with the real world data, the real world system. I'm just going to give that person the last 10 years of data. So this is this is logged policy I'm going to use to design a good policy. Okay, so this is called off policy assessment. It's different from online setting, that I'm like, I want to solve an Atari game. I want to go and in the wild try different things at different situations to see what happens. This is a little bit different.
I get I get that. I get the on policy versus off policy, or online versus off policy. And I also get the, there's also off policy, training where you're developing the policy itself. I get that. What I don't, what's not clear to me is why the assessment or the evaluation is an interesting problem. Like, I'm thinking of it in the context of an inference. Like, you're giving me data, I'm applying my policy, I get some results. Like, what's the hard part there?
Ah, the hard part. So the thing is, so I have multiple policies and I apply them on my data. Okay, and I look at expected value. We know statistically that this estimate of the expected value is going to be close to its mean, to the true expected value. Okay, now you compute the variance. I go and look at the data. I want to compute the variance of the performance of each of those policies. I can do that, and I can come with an estimate that is going to be close to the the true estimate. The first one was the expected value was close to the true estimate with probability, like 1 minus delta. The second one is also close to the true estimate with probability 1 minus delta, but both of them are valid estimate with probability 1 minus 2 delta. Okay, so the probability that these are going to be correct became smaller. Now you are asking me to test 1000 different risk functionals. So all of them are going to be valid estimation with probability 1 minus 10,000 times delta. Okay, so now the question I'm asking is, can we do these things with respect to infinitely many risk functionals? Why I care about infinity risk functionals? Because if I show expected value and variance and CVAR of 10% to an expert might design an arbitrary risk functional that I have not seen before. Okay, so I want to come up with a way to estimate all the risk functionals, performance of my model with respect to all the risk functionals, and make sure that the estimate I'm going to get is going to be a valid estimation. Okay, this was not known before. Like, this is like a new things that people actually show that is possible.
So it's managing the statistical assessment of the policy given a, size of a data set, number of runs, all of that, and trying to get as much information as you can about all of these different things that you care about without compromising the validity of the estimates.
Exactly, that's the exact way of putting it. Yeah. And also one important thing is, I want this all these estimates, which I have infinitely many of them, to all those estimates I want them to hold simultaneously with the constant probability. Okay, so it's like I don't want to compromise at all. I want to get all of them correct. Can I do that or not? So this was not known, now in last 2 years appeared that it's possible.
Got it. Got it. So the fourth trend that you identified, and we'll try to get through this one quickly, is structured MDPs. What's that about?
This is also very fascinating area, which is again aligned with the topic I was saying at the beginning, that the new theme and trend in reinforcement learning is to come up and design more problem specific algorithms. Back in the time I was doing reinforcement learning, I'm still doing reinforcement learning. When I started doing reinforcement learning, we were trying to come with an algorithm which actually works for worst thing ever. Okay. Nowadays we are saying, hey, we are not dealing with the worst thing ever. We are dealing with the world, and world is not as hard as things in mathematics can get. Okay. Why we are coming with our algorithms that are going to work well against the worst thing can ever mathematically happen. Okay. So this is the idea behind structure in reinforcement learning. So last, okay, this is a very old topic, but last 2 or 3 years it became very, very like people got back to it basically. So one of the things is called state abstraction. You're saying that, okay, I have many, many states in my RL setting, RL environment, but it's not like all of them are behaving differently. I can actually cluster them, and they're actually going to behave similarly. So this is the basic, says there is an underlying clustering of the environment, of the observation, that I can use to reduce the complexity of my model. If my environment has 10,000 states, but if I can cluster them, each 100 or 500 of them, and come with the problem with 10 states, I can easily solve everything. Okay, so this is an idea. Let me give you another example if it's possible. So like, let's say I'm here, my job is to go to my blackboard. Okay, so the state of, I can say this visual state I have is my state. So this observation I have is my state. If I move backward, my observation changes. If I move forward, my observation changes. If I turn left or right, my observation would change too, right? But the thing is, this observation is humongous space. It comes from a humongous space. But I can map this observation, which is a big observation, to my current location. And if I know my current location, I know the optimal action is this way. If I look at this direction, I'm seeing different. I'm in different state. But this state or this observation I have is rich enough for me to infer my current location, and I know the optimal action is going backward. Okay, so this is an idea. So when I'm at this state, all this observation I'm looking at, these are different states, but all of them, they can be mapped directly to my current location. And if I know my current location, I know my optimal policy. So this is called rich observation MDP. So it says your observation is rich enough to directly infer your current location. So this is one of the settings that people have been working many, or there are many papers in this area.
And it sounds like it's related to work that has been going on for a while to try to use geometry uh, to reduce the state space from observed pixels to something that's, maybe in this language more structured and that can be more easily operated on.
Yeah. So we have this word model paper. So they are able to get this whole observation of the pixels and map it to the latent state of the VAE. Okay. Which latent state is continuous. Or I have a paper with some colleagues that from Canada and here, that we actually map the whole pixel space to like finitely many states. Or there are many works that they are called by simulation. They actually try to come up with this type of geometric structure of the problem. The, the, there's a friend of mine, David Abel. He's also has done so many works in this area that are actually trying to do a state abstraction. This is one thing, but there are so many other structure people came up with. One of them, which is very interesting, is called linear MDP. Okay, what it says basically things, the transition function in my MDP, despite the fact that I have many states, the transition can be linearized. It can be written in the basically somewhat. Okay, let me say it in some special case. It can be written as a summation of bunch of known MDP basically. So your MDP can be written as a summation of some known MDPs. This way, your Q function becomes linear in the on those feature presentations that you would get from those MDPs. Okay, so this is. Let me tell you this way. Let's assume that your Q function is linear with respect to some feature presentation. Okay, why is good? It's good because, or at least might make sense, is if I'm training a deep Q network, I have a really deep neural network, and the last layer is a linear layer, right? I can assume that this feature representation is good enough that my Q function is linear with respect to this feature representation. Okay, so it actually has some meaning to the in practice. So people have been studying this setting specific in the last 2 years, and it's been like glorified. And there's so many, I think more than 100 papers in this
Oh, wow.
specific area that assumes that there's some linearity structure in the MDP that you can exploit to come up with a good policy. There are people making low rank assumption that the underlying system is low rank, and basically transition function or transition kernel, despite the fact it being like humongous thing, it actually has some low rank structure, and this one has many interpretation. Uh, People are making different assumptions. For example, in meta learning and reinforcement learning, people make the assumption that when you go from one environment to another environment, everything almost stays same, but some linear part of the environment changes. And these are all interesting because these are all easily transferable to deep neural networks.
And so I made the assumption or the statement earlier that a lot of the efforts I've seen, the ultimate benefit is trying to get to sample efficiency and being able to converge faster. Is that the primary benefit of this work, or are there also performance implications or generalizability implications or other implications?
It depends on who you're asking, who writes those papers. Some people just care about the fact that how well they can improve the sample efficiency, and I was part of that crowd many years ago. Okay, but but these days there are other people there. They are like, hey, what makes sense in practice? How things work. We know in practice we can use deep neural networks to come up with a feature representation and do meta learning on just the last layer. If that's the case, can I theoretically study this? So some people, their goal is to theoretically study the thing that they know is going to work in practice, and they theoretically study it and see whether it works in theory, and then come up with their real world applications. Some people mainly care about the fact that whether they can get a better sample complexity. Both approaches are awesome. I love both, but I'm more in the I'm kind of I have one leg in one camp and heavier leg in other camp. Yeah.
Awesome, awesome. So we started this talking about the uh the flashy demos or results or papers that kind of caught folks' attention, and that kind of we abandoned that and kind of went right into these trends, starting with robotics because that was one of those areas. Did we cover all of the areas that you thought were flashy and talking about the trends? Were they all represented in those trends?
Yeah, there's one more trend that I did not talk about. It's I am still not very I would say not knowledgeable enough to talk about, but
Okay.
I see it's a big trend. It's called self-supervised learning approach in reinforcement learning.
Mm-hmm.
Um, that's I'm trying to get myself involved in the sense that to be able to learn what
Yeah.
people are doing and what are the ideas. It's those things I've read so far. They seem to be extremely promising and basically transferring knowledge from different tasks. Again, we are going to the direction of having problem specific approaches. So I have many tasks. Can I kind of do transfer knowledge from one to another? Can I use whatever I learned from one environment and deploy it and get help to improve my performance in different setting? So these are the things that people are doing in this area. I think it's extremely promising and is like is trending, and it's a general theme, is a new paradigm that needs a lot of attention from us. But I'm still a very junior student in that area.
One of the historical challenges or critiques of RL has been that it's very difficult to apply. A lot of the results that got the most press or visibility were, games and other toy problems. What kind of progress have we made in the applicability and kind of real world use cases, commercial developments, that kind of thing over the past couple of years?
Yeah, that's a very good point. Yeah, for supervised learning problems, people just go and plug and play, and things usually work. Merely because those problems are much easier than RL problems. You can now just download one of the implementation of DQN and apply it on some random problem. It wouldn't work. Okay, it's like if you take the implementation of a model which works on the ImageNet and apply it to another image problem, it works. But if you apply DQN, best implementation of DQN, and take it to and apply it to another problem, I doubt it would work. Okay, so it's like we are dealing with the harder problem. There are so many things to be you need to tweak there, and so it genuinely is a harder problem, and because you're solving harder problems, so you need to be more expert. So one thing I'm seeing now is, yes, we have those game stuff who have worked on those game stuffs, basically all the experts in reinforcement learning. Now people are getting reinforcement learning algorithm to work in practice. They are actually experts in reinforcement learning. For example, the robotics setting I'm talking about, people got reinforcement learning algorithm to work in robotics, not because they just downloaded something from GitHub. They learned things, they invented new RL algorithms, those work in their setting. They did not say, okay, let's download this one and run it. No, they wanted to solve the problem. They took courses in RL. I have one colleague who is a roboticist and control theorist who knows a lot of RL, who can just generate and write down many, many machine learning algorithms. He's an expert in machine learning right now. And some of these domain adaptation stuff and meta learning in deep learning stuff I was talking about are basically his work. And he has all the learning theoretic guarantees, and everything is like, if you read the paper, you feel like it's like a veteran of RL theory person wrote it, but this person is like 3 years into the machine learning field, or 4 years. So he's extremely smart and he knows everything right now. So people now working in different areas that are deploying reinforcement learning algorithms learn that, hey, you cannot just download and plug and play. You need to know what you're doing. So people are getting more expert in this area. In recommendation system, people have been using reinforcement learning algorithms forever, and well, they've been making a lot of money in last many. I don't know how many years this has been the case, but in hedge funds have been hiring amazing RL folks and getting RL algorithms to work. They also understood that, hey, in order to make things work, you need to know things very well. So they actually became expert in this area. In many other manufacturing companies that are trying to get RL to work, they also understood that you cannot just download and press run or control R for the machine to work.
Shift enter. Yeah.
Yeah, it was, no, seriously, Sam. It was the case like 3 years ago, 4 years ago. I've been
Mhm.
hearing stories from big companies that people downloaded like DQN algorithm and ran it on random game. I was like, how are you expecting it to work? And they spent like 2 or 3 years to make that thing work, and they failed. I'm like, of course it's not. You need to know
Sure.
the pieces of it.
You're touching on another slightly removed issue. One issue is the ability to take results out of academia and kind of apply them to real world problems and have them easily work. Another related issue is reproducibility. Like I'm downloading the paper and the game that the paper was written to play, and trying to get that to work. And that should be easier in theory.
Yeah, but it's
It
not.
still is hard.
Yeah, it's still hard. Yeah, yeah. Genuinely, this happens because the RL problems are genuinely harder. It's like supervised learning is very tiny, teeny special case of reinforcement learning. And okay, so one thing I tell my students for my RL course is the first lecture is like, hey, do not expect everything to be easy. Any problem you solve in reinforcement learning means that you have solved many, many, many problems in many, many, many fields, because it subsumes many, many fields in machine learning. So it's genuinely hard. And I don't know if we are going in the right direction or bad direction, because we are, at least in academia, what I'm seeing is like we are kind of weak in RL. Not in the sense that we don't know, in the sense that we don't have that many people to train the next generation. I mean, look at France. Like France had so many people in RL 5 years ago. Now almost all of them are not there anymore. Or in US, like we had we had slow growth in reinforcement learning. We didn't have that many reinforcement learning people like 10 years ago, but now we have more, but the demand is much, much, much higher than the number of people we have. So who can give the next the I don't know, the industry or other sections of academia, who can give or who can fit them with new experts in the field? So this is a kind of scary thing, at least for me. I don't know.
Are you still looking for PhD students to
Yeah,
advise?
yeah. Whoever is out there who wants to do reinforcement learning, please join. Yeah, I'm doing everything I can to train next generation of reinforcement learning experts, but it's just me and few others. There aren't that many people in academia who do reinforcement learning, which is kind of not what we want at the moment.
Top predictions for 2022 and beyond.
I would say, well, at least for 2022, I'm sure we're gonna have so many new structure or a structural assumption in Markov decision processes, for example, and people would come up with new ways of modeling MDPs or a special case of MDPs to make them suitable for practice. So I would see that there is a huge wave of experts in the area now. They're trying to cook up new assumptions or new structures for MDP problems to come up with algorithms that actually are more sample efficient and hopefully would help us to design efficient algorithms in practice. Okay, this is one thing I think is going to be one of the main thing in 22. Another thing I'm sure is going to be the case, given the fact that most of the roboticists have been in lockdown and could not go to lab, there's going to be a lot of work, intersection of reinforcement learning and robotics in 2022. uh, I lost track of which year we are. Hopefully the pandemic would be over and we're gonna get back to normal. um, so this robotics is another thing I think is going to be huge. Given these techniques we have in control theory, I think it's going to be one of the main thing in like next few years. That people, there are many, many amazing and awesome control theorists out there. In all the departments you go, ask who is control theorist, you see like, or any university you go, you see like 10 or 20 people they claim they're control theorists. Maybe in 20 is like 5 or 10 people they claim that they're control theorists. Ask who is RL theory, RL expert, like probably you get one. So these people are actually the people in control. They understand the power of this reinforcement learning algorithms and the tools we provide in this area. And I'm sure all of them are going to recognize the power of these things and start to deploy them in their work, resulting in new generation of learning and control algorithms for next few years. Basically, these are some of the prediction, but I'm sure that we are in this direction that we're going, that we are trying to come up with more problem specific algorithms. We're going to have awesome algorithms that are going to provide safe and robust reinforcement learning methods in next 5 years. We're going to have methods in our algorithms that can handle all sort of risk functional that people carry in practice. These are the things that I think people would work on a lot, and also this from practical point of view, coming up with a scenario and settings such that you can have some meta model that you can use. Okay, you can transfer knowledge from different problems to problems that you deal with. This is another thing that I think going to be uh, blooming in next few years. Like in NLP, you have this language model. You can just use it to do many things. We will have something like that not very long in reinforcement learning. Of course, RL is more complex, so you're not going to have one model. You're going to have one model for robotics, one model for, I don't know, dialect systems, one model for Atari games, one model for self-driving cars. So these are the things that are probably going to be the driving factors for the next few years.
Awesome.
Yeah.
Well, Kamyar, thanks so much for running through this with us, and specifically, thanks for all of the work that you put into pulling this together. Uh, Continues to be a fascinating field, and a lot of interesting stuff to talk about.
Yeah, thank you, Sam. Thank you for having me. RL is going to be a fascinating field forever, because it's by definition, if you want to have general intelligence, you need to solve RL first.
Mm-hmm.
It's going to be, and there's so many open problems. I encourage people out there to get involved in reinforcement learning. There's so many open and cool problems to be solved in this area.
Yeah, awesome. Thanks so much.
Yeah, thank you.